Well, I'd like to welcome you all here to the College of Optical Sciences at the University of Arizona for our 2018. I'm stuck in the last century. 2018 Winter School and Workshop, and it's really great to have you all here. I understand a number of you have had some travel adventures, perhaps getting here, or maybe there's still some late arrivals that haven't made it yet. So we apologize for the bad weather on the East Coast, for those of you who are impacted by that, and hope to give you 3 or 4 days, 5 days of wonderful Arizona weather here in Tucson. So what I want to do, I've just spent about 10 minutes to kind of frame what the next couple of days are all about and how we came to this point of creating this workshop. First, I want to welcome you to Tucson. When I got here 6 years ago, it was like the Dorothy and the Wizard of Oz moment where I was like, we're not in Kansas anymore. It's a beautiful state. These are all pictures actually from my backyard. In fact, all these animal pictures are taken from inside my bedroom. And it's just a few of them. So you see animals here in Tucson that you won't see in other places, not only bobcats. And I didn't get the picture of the mountain lion, but we do have a mountain lion as well. Javelinas, which are like kind of wild pigs, pig-like creatures. They're actually peccaries that travel in herds of about 25 sometimes. But then Gila monsters, rattlesnakes, all kinds of exciting animals. So it's an interesting place to be, and I love it here. And I hope we get a chance to convey that to you over the week. This is one of the only times when we're going to just say a few things about the University of Arizona. We have speakers coming in, as you'll see on the agenda, from many of our sister schools in the field of optics and photonics, Creole, University of Rochester, and a number of others. But I wanted to say a few words about the University of Arizona. So we are a large school, about 43,000 students now, and one of the distinguishing features is that we are a Research One university, meaning a very, very large research program, over $600 million a year of annual research funding. That most of that money comes in and it goes to support students and their graduate studies, as well as some significant number of research faculty. And we're typically ranked number 1, 2, or 3 for what they call physical sciences research, which is physics, chemistry, and space science by the National Science Foundation. If you look at our overall research volume outside of all these fields, we're more like in the number 20-ish kind of field as ranked by NSF for public universities. One of the other distinguishing things is that I think we all benefit from here is we do what I'll characterize as kind of big science, meaning in addition to individual faculty research programs, we have large mission-like objectives that we do here at the university. Some of them are associated with space science, so one of the exciting things that we're in the middle of right now is being the prime for a mission to launch a spacecraft, orbit with a asteroid, land on the asteroid, bring a sample back to Earth, and then study it. And those samples will come back here to the University of Arizona for material analysis and so forth. So that's a really interesting mission. When we do these big things, other ones are like these ridiculously large telescopes that we'll expose you to here with some tours, largest optics ever made in history anywhere on the planet Earth. We mold the optics and grind them and polish them and fabricate and test them right here at the university. So these are things that actually get deployed. They're part of systems. Sometimes we're doing this for aerospace companies. And students get to participate in that kind of stuff. So it's kind of neat, and a lot of them have a lot of optics content as well. So for example, in the OSIRIS-REx mission, the camera systems that will acquire the asteroid and then study for landing spots and things like that were designed and fabricated here in the College of Optical Sciences. So here's an aerial view of the university. This is the mall looking down the center of the university. And if you look where we are, we're this set of buildings, 3 buildings right here called the Meinel buildings for the College of Optical Sciences. And we're located at that point right near the football stadium and right near the basketball stadium, which makes for interesting parking when we have game days and things like that. We sometimes refer to ourselves as OSC, and if you wonder why that's the case, it used to be a center, a graduate research center. Our origins were about a little over 50 years ago, back in '64. It was a enterprise that was created to have more graduate degrees, graduate program in optics and optical sciences. Very strong foci in optical physics and in optical engineering, and that continues to this day. So here we are, and despite what you see this morning, we are usually very sunny. I looked at the weather map, and I think by tomorrow you should see some of the blue sky that I showed you on this intro picture here. Hopefully tomorrow will look a little more like that. So a little more about our college. We have about 60 faculty, maybe 35 are tenure track faculty, and about 25, 30 are research faculty. In addition to that, we have a lot of faculty on campus that are joint appointments in other colleges. So College of Engineering, departments of electrical and computer engineering, material science, biological sciences, and so forth. And they have a footprint here in the College of Optical Sciences as well. So it's kind of like we have our tentacles spread all across the university and very woven into a lot of interdisciplinary programs. And our faculty are very, very accomplished. A lot of them are in the national academies. Many have been presidents of the professional societies like the Optical Society of America, the SPIE, and so forth, and fellows of these professional societies as well. If you look at our graduate student body, we're about 3/4 graduate students. So we have an undergraduate program that doesn't start until the sophomore year typically, because we don't recruit people out of high school into optics, and I'll get to that in a minute because nobody seems to know what optics is. Instead, we steal them out of science and out of engineering in their sophomore year and seduce them into the College of Optical Sciences. And so we have 3 classes, typically 35 a class, something like that. Maybe now it's up to about 40, something like that. So about 120 undergrads typically. And then about 200, 190 or so PhD students resident here at any given moment, and about 100 master students, 120 master students, something like that. We also have a distance learning program, and if you look cumulatively, this is a little bit outdated. It's over 2,800 right now, degrees granted since we were launched in 1964. And if you look at our cumulative students graduated or the research volume, meaning dollars, how much research contracts do we have at any given moment? We're the largest optics program in the United States. If you look at our college, we don't have departments. So typically a college has a department of this and a department of that, and so forth. We're one kind of big department, a flat organization, and we have research areas, research themes, research groups. 4 that are shown here, and throughout this winter school, you'll hear presentations from people kind of giving you a glimpse of what's going on in these areas. And I want to point out that this is not a sales pitch for the College of Optical Sciences. I'll get to the purpose of this workshop in a minute, but we will expose you to these areas through kind of survey talks to give you a sense of what this is all about. And the 4 areas are optical physics, optical engineering and design, image science, and photonics. And rather than dwell on these now, I'll let that unfold as this workshop goes along to give you a sense of what these different areas are all about. So why are we here? First, I want to credit the organizing committee for pulling this together. So it's a group of our faculty who worked very hard to develop the agenda, get out the invitations, and get your participation. We have an external advisory committee that I'd like to acknowledge, and especially acknowledge our sponsors, who are the ones that are bankrolling your ability to be here. A lot of you are supported financially to travel and to pay for your expenses while you're here, and that comes from contributions from these organizations shown here. So it's very generous of them, and it's because they believe in what we're trying to accomplish here. So optics and photonics, what is it? Actually, one of our students made a wisecrack that I like to reproduce. It's Colton came out and said, "Well, they're everywhere you look," and of course that's a pun because of vision and so forth. But it's really true. Optics and photonics are everywhere. One of the things we all experience as faculty here is we sit on the airplane and people say, "Well, hi, what do you do?" "Oh, I'm in optics," and they go, "Oh, okay, yeah, I mean, eyeglasses," and we kind of go, "Well, yeah, maybe." And they ask, do you have any of those little screws that I can get to fix the hinges? And so part of our goal here is to give you an exposure to what we mean by optics and photonics, and really how broad it is. And it's incredibly broad. So the objective of this winter school and workshop is to give a select group of students. So you've been chosen by your faculty advisors and at your schools as being students that have expressed interest in research and in further education and graduate education and potentially in optics and photonics. And we want to continue to lure you into the field because we want the best talent in the United States or in the world to go into the field of optics and photonics. And to do that, we want to give you a better sense of what it's all about. So that's really, to first order, that's what this workshop is all about, is to help you understand what your opportunities are in this field we call optics and photonics. And also to expose you to research. And I know you've all been involved in some way, shape, or form in research. For me, if I were to define research, it's trying to do something that you don't know how to do. And whether that's fundamental science, asking a question, I don't really know what's going to happen if I do this. I think I know, but I don't really know. Or I'm going to engineer a solution that nobody's ever done before, and I got some harebrained idea about how I'm going to do it, but you don't really understand the problems until you set out and actually embark to try to do something new that's never been done before. So that's research, and that's really what we're all about here at the College of Optical Sciences, and that's kind of what we want to talk to you about, what your opportunity would be as a graduate student either here or at any of our sister institutions across the country in the field of optics and photonics. For me, it was a life lesson when most of my career was at Bell Labs. And I used to be the guy on the blackboard who would analyze things, and I'd go through the numbers, and somebody'd say, "Well, we want to do this," and I'd go, and I'd crank, and I'd go through, and I'd show them why it wasn't going to work. And people would go, "Oh, okay," and then I'd go through and I'd do it again. And at some point, somebody really drove the nail home for me that if you don't go try to do something, even if you think there's issues with it and you don't have all the questions answered, even if you're skeptical, if you don't get in the lab and try to do something, you won't make discoveries. So part of research is also about just getting in and dabbling and trying to do something, because a lot of the excitement and unexpected discoveries come along the way of trying to do this, and along the way you discover that, and you turn and you go do something different. If you're not trying to do stuff and you're just sitting in your office calculating, analyzing, designing, you rarely would get that opportunity to be exposed to those unknown things. So participating in experimental science, working as a theoretician, supporting experimentalists and so forth, that's what it's all about. So here's a little breakdown of what we've got here. A lot of participating institutions, and now it's expanding to some of the core research universities in the country like UCLA, Caltech, et cetera, UNM. In the past, it had been primarily focused on what we call primarily undergraduate institutions, so strong undergraduate programs in physics and so forth, but not a lot of graduate research. So students at those universities may not get as much exposure to what the graduate research programs are typically all about. We also have a lot of external faculty and research staff here, research scientists coming. Here's what the agenda looks like over the next couple of days. Very full agenda. Tonight we'll have dinner at a restaurant in town. You'll see me again at 3 o'clock. I'll give a talk on photonics, which is one of those 4 areas I talked about earlier. And then tomorrow, again, it continues, a full day, and we have lab tours throughout the day, including the well-known, famous mirror lab we have here at the university for fabricating these absurdly large mirrors. And you'll hear some talks that describe some of that technology as well. And then it switches gears to the winter workshop, where a lot of faculty will be joining us for the weekend to talk about educational programs and how research can complement educational programs in the field of optics and photonics. And this is an eye chart. You're not supposed to read it. I think all this stuff is in your materials, though. There's 2 full days of talks, and these include presentations from, as I said, from our sister schools at Rochester, Creole, and a number of other places, as well as additional research talks describing different areas. And again, nice dinners, a banquet dinner on Saturday night. And don't be fazed by that name, Culinary Dropout. That's a name of a nice restaurant here in Tucson. So that's it. The one additional thing we have this year is a Immersion Day, and a number of students, I think, are participating in that. Not everyone is, but it's to really get in the labs of some volunteer faculty to actually participate in research, not just see the labs, but to actually assist in the ongoing research that's taking place in those labs to give you an even deeper sense of what it's all about. So thank you. Again, I welcome you all here. You'll have lots of opportunity to meet with us over the next bunch of days. There's dinner events, there's social events, there's lunches, there's poster sessions, there's lab tours and so forth. So if you have questions, this is supposed to be really informal. I should cut this tie off and chop it. It's supposed to be a very relaxed atmosphere. It's a neat chance to get to know some people that you quite likely will run across throughout your lives. Look to your left, look to your right. Some of these colleagues, even if you don't end up at the same place, you'll get to know each other as fellow researchers and members of the optics and photonics community. So welcome to that community. And I'm going to kick this off now and introduce Jason Jones, who's not only one of the key organizers of the session, of the whole workshop, but also the first presenter who's going to talk to you about optical physics. So thank you. I don't know if you noticed my nifty laser pointer. How do you think it got to be yellow? There's actually 2 lasers inside this thing that are adding their frequencies using some frequency mixing. You're used to seeing the green ones that do frequency doubling, but this one's even more exotic than that. I got it for free. If you went to buy it, they're probably about $400.
I'll stick with the red laser pointer. So good morning. Yeah, my name is Jason Jones, and I also want to welcome you, and thanks for coming. We're excited to have you all out here and get to know more of you individually throughout the next 4 or 5 days. We just tested this, and it worked fine. Let's give it another shot. So as part of the structure of the sort of the winter school portion of this event, we have different types of talks. We'll have sort of an introduction to these different areas that Tom mentioned. So I'm going to be giving an introduction to optical physics, where we'll have a little bit more discussion on what are some of the topics that we cover, in a graduate level curriculum in optical physics, and then also a little bit about some of the research area. And in some of the other talks, we'll maybe focus more on specific research areas and things like that. So Tom's mentioned this already, the different fields in optical science that you might consider going into: optical engineering, photonics, imaging science, and optical physics. And so we'll have some talks introducing photonics and imaging science and optical engineering throughout the next 2 days. So these different fields, of course, all rely on different models of light. Right? And we can describe light in many different ways. Right? So we can think of light in terms of geometrical optics. And it's an approximation of what light is, but it's a very convenient one if you're trying to figure out how to trace rays through a complicated lens design system, for example. You want to focus on what are the aberrations in the system. You might not want to go to a quantum mechanical description of the light field. Right? You want to efficiently get to that answer, so you can treat it as a ray. If you're looking for other phenomena, such as diffraction or interference effects, it's probably better to treat light in terms of physical optics description, where light is a wave, and you have wave-like phenomena, right? Interference and diffraction. And we can also treat light from a quantum perspective, where we can treat light as either a wave or a particle. And so these are different models for how we might describe light. And in optical physics, it's sometimes light and it's sometimes particle. Right? And we're not just interested in the light field in optical physics, but we're also interested in the interaction of the light field with matter. And there's different models for the interaction of light with matter, and you may be familiar with some of these already. There's the classical picture. The simplest model is to treat light classically, as electric field, electromagnetic field, and to treat matter as a simple classical device, a simple harmonic oscillator. And so that's known as the Lorentz oscillator model. And I'll look at that briefly and some of the phenomena that it describes. And there's a semi-classical picture where you get a little bit more information. You still treat light classically, but you treat matter or the atom in terms of a quantum mechanical model. Right? So that's the semi-classical picture, and it's a very powerful description of light-matter interaction. But it doesn't give you everything, all the phenomena that you might want to look into and understand in optical physics. So there's a full quantum picture in which you treat both the light field and the matter itself in terms of a quantum mechanical model. Right? And that gets into the field of quantum optics. So what I want to go over in the next 50 minutes or so, 45 minutes, is to review some of these different models and then talk about some of the things that they describe and some of the things that we use them for in research. And this is all things that are covered in an optical sciences curriculum that you would cover in the optical physics portions. So the first is this idea of the classical electron oscillator model. Just bounce through a couple descriptions of it. Some of you maybe have seen it. What does it describe? What does it tell us? And then where does it fail? What does it not tell us? What would you need to know and dig deeper if you want to look at other phenomena, study other things? And then that's the semi-classical model. And what does it describe? And then where does it fall short? And then the semi-classical model is a very powerful model, and it's pretty good at describing the basic operations of the laser. Not everything. We have to ad hoc add a few things to it. But we'll look at basic laser fundamentals, and then rather go into a survey of different laser types, and we'll have another talk talking about lasers specifically. I want to give a few examples of how these models can actually be tested using lasers as precision tools. So I'll talk about a couple applications of lasers that we use in my own research group as well. That's a little overview. Feel free to stop with any questions along the way. Okay. So the classical electron oscillator model by Lorentz, very simple. We reduce the atom to just mass on a spring, right? We assume the nucleus, the proton in this case, is very, very heavy and fixed, and the electron is bound by some spring. So this isn't a good model for the atom, but it turns out to be a very good model for the response of the atom to the light field. Right? So just a few equations, since we're calling it a school, and just to refresh your memory on what this is. So we have a position of the electron relative to the proton, right? And so we just look at the forces on the system. So in this case, we're modeling it as a simple electron on a spring. So the force on the atom is really just this Hooke's law. We have a spring constant K. And we can write that spring constant K in terms of a natural resonance frequency and the mass of the electron. And then we also have the light force, right? So that's the Lorentz force. And so we have the electric field of the light. Ignore the magnetic component. And then we have the charge of the electron. And then, following Newton, we just add the forces and set them equal to each other. Right? So the total force then is just mass times acceleration. And these are the other two forces. And so we have this nice differential equation describing how that electron is going to move when it's under this classical external force. Right? That's the simple Lorentz model. Now let's just for the moment say the light field is shut off. Just remind ourselves what happens if the electric field goes to 0, then we just have a simple harmonic oscillator, right? So we remember what that looks like. The solution's trivial, and we just have this nice cosinusoidal oscillation of this electron responding or oscillating. Now, in a real atom, is it going to oscillate forever? It won't, right? It's going to decay through different mechanisms. And so we have to add a damping force to get a better description of how that atom is going to respond. Does anyone recall or might guess what might cause damping of that simple oscillation of the electron? So it could collide with another atom, right? They're not isolated. So if it collides, it could lose the energy or it could dephase it. There's also spontaneous emission, which is a quantum effect. But we can include it in the model, and we can assume that there's some decay. So in the Lorentz model, we also have a damping term. You don't necessarily identify what it is, but it's due to these other effects that, phenomenologically we know exist. So you can add those elements into the model. And then you get this nice damped but driven simple harmonic oscillator. Right? Second order differential equation, but it's a very powerful expression that tells us how the position of this electron is going to change in the external field. Right? And what we can get from that, then, is a lot of useful information on light-matter interaction. So we have a dipole when we have this charge separation. And the position of this electron, x, is what we solve for in this expression. Right? So if we solve this Lorentz model, we'll have position of the electron. That gives us the dipole moment. If that dipole is oscillating, an oscillating charge gives off dipole radiation. Right? And so that gives rise to different effects such as absorption or the index of refraction, right? The phase shift of the light as it travels through a medium. So, for example, if the light's driving this oscillator and it's in phase, and the dipole radiation is emitted in phase, and it might affect the phase of the field, and that's effectively what the index of refraction tells us. If this dipole is oscillating out of phase, which happens on resonance, then you're going to get destructive interference between the light field that's driving it and the dipole radiation, and you'll get effectively absorption of that light field. Okay? So the simple Lorentz oscillator model does a good job of describing the index of refraction, and specifically, if we look at the real and imaginary components of the index of refraction, describing absorption and dispersion. Right? And so here's an absorption profile at the resonance of this spring. And here's the associated index of refraction about that same resonance, right? How that changes and varies. The simple model gives rise to different phenomena such as Rayleigh scattering. And that scattering increases as lambda, as the frequency to the fourth power. Right? And describes phenomena like why the sky is blue and why the sunsets are red. Another example might be the ordering of the rainbow as it disperses through a prism or a water droplet. Right? Glass, for example, has strong absorption in the ultraviolet. And in the tail of that strong absorption, we see the index of refraction is going to vary such that it's larger for blue wavelengths and lower for red wavelengths. Right? So the simple Lorentz model describes why the blue light is bending more out of a prism, for example, than the red components. If we go to a system rather than a single electron and a proton, if we look at a larger object like nanoparticles, where you have a collective charge on a sphere, you can get a different effective spring constant for the collective motion of all the charge on the surface. And you can vary the spring constant now, and therefore vary the resonance of that system by changing the size of the particle. So these are examples of different gold nanoparticles. And the Lorentz model does a really good job of predicting where the resonance of these different sized particles would be. And that leads to absorption at different colors, and that leads to the different appearance of the different gold nanoparticles. All predicted very well by this simple model of light-matter interaction. But it does fail to predict some very important things we need to understand for laser operation, for example. Any guesses what we're missing in our model for light-matter interaction? What other phenomena are important in describing laser action, for example? Exactly, stimulated emission. Not described by the simple model. Or the saturation of absorption. Right? In this simple classical electron oscillator model, we can drive the atom harder and harder with our light field, and it just scatters more and more light. There's no saturation. There's no optical gain, stimulated emission, or spontaneous emission. Right? So we need a better model if we're going to try and understand basic laser operation. So what we start with is a better model for the atom itself. And that gets us into the semi-classical description. But let's step back and review then what a better model for the atom might look like. And so I think many of you have had quantum mechanics, maybe not all of you. How many of you have had an introduction to quantum mechanics? Okay, good. So let's just highlight a few things that one might cover in a more advanced graduate course to try and understand the basic components to what a better model for the atom might look like by utilizing a quantum picture. So we'll talk a little bit about the famous wave-particle duality in quantum mechanics and what a wave equation for matter might look like. It's very similar to the wave equation we have for the light field. And then finally, what a quantum description of the atom might look like. It's really a beautiful thing. You go through it very thoroughly in a first-year graduate course in optical physics. And you might have gone through it in a more advanced course as undergraduates already as well. Well, anyone recognize this guy? No? Okay. Louis de Broglie had a famous postulate back in 1924 on this wave-particle duality for matter. And he came up with de Broglie wavelength. And he actually did this as part of his PhD thesis. Right? So that would be rather intimidating if you're plugging away at your thesis and the person next to you is proposing something that turns into a Nobel Prize and disrupts the scientific world. That's setting the bar pretty high. But it was part of his thesis, and it was a prediction that matter should have wave-like particle properties, and that the wavelength for matter is going to go as something called Planck's constant divided by the momentum of the particle. So this was a very huge departure from the classical pictures at the time. And the question, of course, is what is waving here? What is the wave-like property of nature, and what does this wavelength really mean for a particle? Right? Think about a single particle. So we can look at an analogy with light and what we might expect from light, right? Or classical waves, for that matter. So a really classical picture of interference with wave-like descriptions is this diffraction from two slits. Right? So if we have a plane wave of light or water, and it's incident on two openings, then because of the wave-like nature of the field or whatever the description is, the path length taken from this slit to some point and the path length taken from this slit to that same point will be different by this little amount here. And because of that difference in the two waves, they're going to have different phases when they reach this point. And so they're either going to interfere constructively or destructively. And that gives rise then to this interference pattern you would see from ocean water or from a light field going through slits. So if this is a description of an effect that waves have, it must also be true if there's wave-like properties for matter. See if I can run this. So experiments have been done to test this hypothesis for a long time, and they're quite striking and startling, right? Because with particles, it's easy to think of them as individual things, right, that can't interfere with itself. So this is an experiment where we have two slits, and an electron is sent one at a time through this screen. Okay? And then it's detected individually, one at a time. Now, you would expect that for a single particle, it's going to go through one slit or the other slit, and that's it. And it would detect it somewhere on the screen. And that's pretty much what you see. But as you build up this pattern statistically, and you look at a large ensemble of this event, you start to see the interference pattern that you'd expect from waves that are passing through two slits. The only way to explain this type of phenomena is that the particle never passed through one slit or the other slit. There's no other way you're going to get to it, a way to explain why this diffraction pattern could build up. And this really gets at the wave-like property of matter. The fact that the particle can also be described as a wave. We call it the wave function. And that in some sense, it didn't go through one slit or the other slit. And that it was only detected and it was only localized after it was detected on the screen. And so there's something about it that's wave-like and went through both slits at once and interfered with itself. So how do we properly describe or understand that? Because it's completely non-classical and non-intuitive. Right? So let's just look at two postulates. There's more than that in quantum mechanics that you would go through and try and get a full description of a quantum picture for matter. And the first key one is that the wave function, whatever that is, for a particle tells us everything that you can possibly know about the particle. If you can write down the wave function, you know everything that's knowable about that particle. Okay? And how do you interpret that? Well, this is the technical details of how you interpret it. It's called Born's statistical interpretation. So this wave function is interpreted as a probability amplitude. And if you take the modulus squared of the wave function, it tells you something about the probability of finding the particle in a certain region of space. Right? So that's how we kind of define this wavelength property describing the particle. So if that's the wave function, then there must be a wave equation that governs how it propagates through time and space. And we can look at an analogy with electromagnetic field, right? For the electromagnetic field, we have Maxwell's equations. And from Maxwell's classical equations, we can write down a wave equation for the light field, right? And this equation for light tells us how light propagates through space. It gives us things like plane waves. Plane waves are a solution to this wave equation. Or spherical waves, also a solution to this wave equation. And that's fairly easy to digest, right, compared to particles. So a second postulate of quantum mechanics is that this expression, known as the Schrodinger equation, is the wave equation for the wave function for matter. Okay? And so by solving Schrodinger equation, we can understand how we can solve for what the wavelength properties of the particles would be. So that's the wave equation for matter. And if the potential that the particle is under is time independent, then it simplifies even more, and you will learn something about that's called the time-independent Schrodinger equation. Okay? And the time-independent Schrodinger equation looks like this. There's an operator, the wave function, and that's equal to the corresponding energy of the system times the wave function. Okay? We won't go into it in much details, but that's the equation you would solve for a given problem. So we can look at one trivial example, and that's just a free particle. Right? Free particle where this potential is zero. Right? Just a free particle in space. The differential equation looks very simple. In fact, it looks just like the wave equation, where the solution now is just a sine wave. Right? Instead of the wave vector k, which is related to the wavelength of light, now it depends on the energy of the particle. And so we also have plane wave solutions for particles, just like we have plane wave solutions for a light field, described by this wave function. Okay, so that was a little segue into introduction to quantum mechanics, but this can now be applied to our simple model for the atom. Right? So now the potential for the particle is the electron, and the potential it's in is just due to the Coulomb potential. Right? That's just 1 over r. Right? So we have a proton. We assume it's fixed, it has a positive charge, and we have some small light electron around it with a negative charge. And we plug this Coulomb potential energy function into the Schrodinger equation, and you can solve, actually analytically, what the energy levels must look like and what the wave functions would be. Okay? And so this is just a plot of the Coulomb potential. This is the 1 over r potential. And this would be the ground state energy for the atom, the first excited state energy for the atom, and so forth. Right? And you can get this nice expression, what the energy is. If n is equal to 1, then it says that the ground state energy for the simple atom, which is hydrogen, 1 electron, 1 proton, has a binding energy of minus 13.6 eV. Put that into wavelength, that would tell you that you need light at 120 nanometers in order to excite the atom from the ground state into the continuum, or to ionize it. 120 nanometers is in the vacuum ultraviolet. That's hard to generate. But this is actually an analytical solution that you can get for this very simple hydrogen atom. And it's really a beautiful solution because it predicts so many things so accurately. And there's not many solutions you can get analytically that have such a nice model and can be used for so much physics. And we'll show you a little bit of that. There's also then the Rydberg formula. It just tells you what the wavelengths are. So I already mentioned 120 nanometers would be the ground state ionization wavelength for hydrogen. And the point I want to make here is that this simple model, analytical expression for the hydrogen atom, right, the most basic element in the universe as far as atoms go, can be directly tested with spectroscopy, using lasers to excite these transitions. And so we can use lasers to directly test quantum theory. And a lot of early quantum theory was tested just that way. If this Schrodinger equation predicts these energy levels, let's go in and see it. Let's go in the lab and measure the difference between these two energy levels with the laser and see if that's exactly the energy, or is there a small shift and it's not quite right. And if it's not quite right, is it because our laser's not quite right, or is it because the model's not quite right? So those are the type of things that can be tested. And of course, that simple picture doesn't tell the whole story. But it was an excellent starting point. But the atoms are not quite so simple, right? Even the hydrogen atom is not so simple. Part of the problem is that first transition's at 120 nanometers. And as we'll see, it's hard to build lasers at 120 nanometers. There's other things that complicate it. First of all, that electron that was in our simple Lorentz potential isn't just a simple charged particle. It has another property called spin that you might have heard of. Right? So it has a magnetic moment as if that electron were spinning around. But that would be the classical picture. And in fact, it can't be described that way. But it does have this property that it has a magnetic moment. And that magnetic moment interacts with the angular momentum of the electron. And so you get this interaction energy. And the point is, when you look more closely, this first excited state, this first energy level of that atom, gets split into two energy levels because of the spin of the electron. So you can adjust your model and try and account for that. And you look a little bit more closely, and you find that, oh, this energy level here is also split due to another thing referred to as, due to vacuum fluctuations referred to as a Lamb shift. And then you look more closely again with higher resolution, and you see there's another splitting. And it turns out that that's due to the fact that, well, not only the electron has spin, but the nucleus has spin. And so the model has to be refined more and more, and the experiments have to become more and more precise to see these small splittings and shifts. So the point is that precision spectroscopy can be used for testing fundamental optical physics. Now, this is something that has been starting, back since the beginning of quantum theory, using light sources to test quantum models. But it's not something that people are just doing in the 1930s and everyone knows the solutions to now. Even to this day, there's big puzzles in terms of descriptions of these systems. One of the biggest puzzles right now in this area is what's the size of the proton. Right? It seems like something we should know by now. And we know it pretty well. But the problem is there's two different very good, accurate experiments that measure very, very different, many sigmas away, results. Right? So even today, there's this problem of what's the size of the proton? Right? What's the charge radius of the proton? And one way they're testing that is with spectroscopy. They'll look at simple hydrogen atom, and then they'll create something called a muon, where they replace the electron with a muon, same charge, different mass. They do the same measurement, and they back out what the electron radius should be, and they get a different result, and no one knows why. So these precision tests are still very active in the field today. It's not something of just the early founders of quantum mechanics were using. So now that we have this better model for the atom, these different energy levels, briefly overview what we call the semiclassical picture. Right? That's where we still have a classical light field, but now we use this quantum picture for the atom. So we use the Schrodinger equation as before, and we have the potential now is not just the Lorentz potential that the electron's in, but now it has this external driving electromagnetic field, the light field. Right? But we still treat light classically in this model, and you'll go through the steps in the curriculum solving the Schrodinger equation in the presence of both the Coulomb force, I think I was saying that wrong before, and the Lorentz force. And of course, there's a lot of stuff involved in that. So rather than going through it, I'll just show you sort of a numerical solution of what the atom looks like in the semiclassical picture, or rather what the wave function for the electron looks like in the semiclassical picture when you turn on a classical light field. Right? So classical light, quantum matter. It predicts things known as Rabi oscillations and a whole other host of phenomena. But let me try and show you briefly what it might look like. All right, so here's a picture of the hydrogen atom in the ground state. Right? So the red is describing, you can think of it as sort of the smeared out charge of the electron, but it's really the wave function or the probability amplitude for the electron. Okay? And so we think of it as a round thing in the ground state. Okay? Now, we're going to turn on, it shows right here, Q times E. So E is the electric field, it's pointing down. And when you run the simulation, it'll solve for what the semiclassical model for what the atom is going to look like in the presence of the light field. Right? But it's a classical light field. So if I turn this on, you can see the electric field oscillating back and forth. So it's linearly polarized light. And you see the response of the atom to that light field. Now, if we were to stop and make a measurement at any one point, quantum mechanics would tell us that we're either going to find it in the ground state or the excited state. But this is the probability of where it is. And up here, it shows the energy. And if we were to stop and shut off the light field at just the right time, then we would actually be in the first excited state. Right? So this is what the wave function would look like for the first excited state of the hydrogen atom. Okay? And so a chemist might call these different orbitals and things like that. So this would be the 2p first excited state of hydrogen atom. So now with a laser, according to the semiclassical picture, we can turn on a light field. And if we shut it off at just the right time, we can be guaranteed to put the atom in the first excited state. And according to the semiclassical picture, it should stay in that excited state. So now we should be able to predict things like optical gain, because we can put atoms in the excited state, and we can have stimulated emission. If instead we leave the light field on, oh, by the way, the red line here is showing you the average energy that the atom has at the time. Right? So this is the ground state energy, this is the excited state energy, and this white curved line is just that 1 over r potential energy that the electron feels. So if we were to leave the light field on a little bit longer and then stop it at just the right time, the atom would have gone from the ground state into the first excited state back to the ground state. So if you can imagine a pulse of light that you shut off at just the right time, the semiclassical picture would predict that it doesn't get absorbed. The atom goes from the excited state to the ground state, and after the light goes through, the total energy is the same for the atom. So there's no optical absorption. And that's actually a phenomenon that can be tested. It's called self-induced transparency, where just the right pulse of light can go through something that would normally absorb it, but it can pass through unabsorbed. And that's a prediction of the semiclassical theory. It's really describing a coherent interaction between the light field and the atoms. Yes?
Is there any reason why it changed from red to green? Or was that
Well, partially to keep people awake, right? But the colors are actually representing the phase of the wave function. So the wave function has an amplitude and also has a phase because it's a wave. And in fact, on that point, if we were to go through and look at excitation by circularly polarized light, it would drive it to a different state. Right? And your question reminded me of that. Now you can see we have circularly polarized light, and you can see how the atomic response is different. And now you get even more colors. Because it's going into a first excited state, it's the same energy in the simple model. But if I stop it when it gets up there, in this state, the 2p state, it would have the same energy, but it now has this phase wrapping of the wave function. And you can relate that to actually angular momentum of the atom when it's in the first excited state. And how did the atom go from the ground state with no angular momentum to this first excited state with angular momentum? Where did that angular momentum come from? It came from the light field. So light can also carry angular momentum. And so it absorbed some light, and it got the energy from the light field, and it also got the angular momentum from the light field. And you can see the phase of that wave function in those different colors. Let's see. My PowerPoint disappeared on me. There we go. Okay. All right. So just review. So the semiclassical picture, first of all, gives us an atom with discrete energy levels, and it describes the simple idea of optical absorption. Right? So there's energy in the light field that goes into the atom. If we shut it off, the energy is in the atom now, so that's optical absorption. And it can also now give us optical gain, or stimulated emission, because this process is completely reversible. If the atom's in the excited state and we turn on the light field, we can drive it down to the ground state, like we saw. So what happens to the energy that was in the atom? It goes into the light field. And that's the basic idea behind stimulated emission, or optical gain. It can also describe saturation of the absorption or gain. Right? If all the atoms start going up to the excited state, then the absorption is going to decrease. And eventually you'll get to the point where you have just as much absorption as you have gain. Right? So that's a saturation of gain. So it does a good job of describing a lot of the basic components you need to understand a lot of different phenomena, including lasers. It doesn't describe everything. It's still lacking. And one of the key things would be spontaneous emission. When that atom's in the excited state, the semiclassical picture just says that it stays there, unless maybe it bumps into another atom. Right? But there's no spontaneous emission. To predict spontaneous emission, one would have to go another step and have a quantum picture for the light field itself. We're just treating it classically here. And if you have a quantum picture for the light field, then it will predict and fall out of the theory that an atom is going to spontaneously emit photon once it's in the excited state and decay, even if it doesn't collide with anything, even if it's in what we think of as a vacuum. So, and that would get into the field of quantum optics. So with time remaining, let's then just review basic elements of a laser then. That's very well described by this semiclassical theory. If you just add the expectation that there's going to be spontaneous emission, right, which is truly a full quantum optics effect. So lasers, so what are the basic components? Well, we need gain, right? So now we know that we can have gain. We have light coming in. We need atoms that are in the excited state so they can give up that energy to the light field and amplify the light field. So how do we get that? Well, we need some sort of pumping mechanism, and we need an atom with a couple different internal energy levels. So if we just look at 3 energy levels, let's say our atom's in the ground state, we have to have some way of providing energy and pumping it up to the excited state. Now there's going to be spontaneous emission. That's not in the semiclassical picture, but we know it exists. That takes us down to another level. And hopefully it sits there long enough until we send our light through it to be amplified. And when the light field comes, it can stimulate the atom to emit a photon, and we get optical gain. So we need to have some optical amplifier material. We need a pumping source to create population inversion. And then we need a feedback mechanism in order to take the light that was amplified, send it back through again. Right. And so we use optical cavities for that. So lasers, although they're called light amplification by stimulated emission of radiation, that's really an amplifier. It's really an oscillator. Right? It's a closed system. It oscillates back and forth. But that acronym, light oscillation by stimulated emission of radiation, isn't quite as motivating. It's called a loser, so they stuck with laser. So optical cavities, wonderful field. You learn a lot about optical cavities. This is just classical light field governed by the paraxial wave equation. And the solutions mean we can have all these different modes appearing inside the laser cavity. The basic operation of the laser then under steady state operation is that it requires population inversion. So we start pumping the gain medium. We get population inversion. And now what happens is we get some spontaneous emission. Right? So light, in spontaneous emission, it can go in any direction. So photon might go off in this direction, some might go off in this direction. but some's going to go along the axis of these two mirrors in this optical cavity. And so eventually, you'll get some spontaneously emitted light that starts going back and forth in the cavity. So it builds up from spontaneous emission. And each round trip, it sees a little gain by stimulated emission. And that's going to continue to go, and the light field's going to build up and up and up until it's so intense that it starts driving a lot of that population down to the ground state by stimulated emission. And so eventually, you'll reach a steady state where the population inversion you're creating with the pump laser is matched by the stimulated emission from the light field. So it basically saturates. And you'll get gain is equal to the losses each round trip, and that's a steady state operation for the laser. And you have a very intense field in here, and one of these mirrors will be partially reflecting. Maybe it's 95% reflecting, 5% of the light sneaks out. So with these lasers, one can generate extremely monochromatic, highly coherent sources of light. And that is a powerful tool because you can control the frequency of the light field very accurately, and you can tune it by changing the cavity length. And you can now go back and use this device to probe all those energy levels and test some of the basic fundamentals of quantum theory. So rather than going into talking about different laser systems, let me just, in the last few minutes, talk a little bit about lasers as precision tools, not as Death Star weapons or anything like that, but of course they're also used to shoot down annoying little toy planes and things like that. Right? So let's look at a few applications of precision spectroscopy using lasers to make very accurate, precise measurements. One of the applications is for next generation atomic clocks. Okay? And in order to do these type of experiments, which I'll just briefly talk about, there's a new tool that in my group we use quite a lot, which is the so-called femtosecond frequency comb. And I think it's also very hard to generate light in the vacuum ultraviolet and extreme ultraviolet. But I'll probably skip this last part just on the basis of the time remaining. But we do have our labs open today, and we'll be happy to tell you more about that later. Okay? But let's just talk about this precision tool for atomic clocks. So precision spectroscopy, I like to say it's unveiling and has often unveiled the quantum world. So back in the days of Newton, they didn't have lasers. Right? So they used dispersive elements like prisms to separate light and to analyze the content of the light field. Right? And so there's these famous Fraunhofer lines. And you look at the emission from the sun, and you see there are certain bands that are missing. Right? This is due to absorption in different atoms and molecules in the Earth's atmosphere and the atmosphere of the sun. And these are discrete energy levels, right, predicted by the semiclassical theory. So these have been used for a long time now to test where the resonances of different atoms and molecules are in this broad spectrum provided by sunlight. But then you think about, well, how accurately can we test these theories? Well, using spectroscopy, it's going to depend on how well you can resolve the different colors, right, to see two really closely spaced transitions. And using dispersive elements like prisms and gratings, you're limited to a resolution of the order of 10 to the minus 7. It means you could get, if you were to say, well, what exactly is this line right here? I could give you 7 digits on what the frequency or what the wavelength of that light is. But to really dig in deeper and to test these theories, you need a higher spectral resolution. Okay? So with the advent of masers operating in the microwave region and lasers in the optical region, a dramatic shift in the precision with which they could test these theories. And now you can get spectral resolution on the order of part 10 to the 15th, meaning I can tell you 15 digits, and now I think it's out to 18, exactly what the frequency of the light is or exactly what the resonant transition of a particular atom or molecule is, right? Because of the purity of these laser sources. And these can be test fundamental things like variation of what's called the fine structure constant, or this proton charge radius problem that still exists. Right? So these are some of the things you can study using highly stabilized lasers in precision spectroscopy. This is just an example of sort of the state of the art with CW lasers. Just stabilizing and trying to make the laser highly coherent is still an active area of research. So nowadays you can send a light field to the moon and back and know exactly how many oscillations have occurred without skipping one single cycle. of the optical field. Right? And this is just an example of beating two lasers together and look at the difference in the frequency of two lasers. This time scale is 30 seconds, and it hasn't lost one optical cycle over 30 seconds. So these are extremely precise tools that can be used for testing what the atomic transition frequencies are. And so that leads right into atomic clocks. Right? So on all the satellites, we have atomic clocks that are based on microwave transitions. Right? So what is an atomic clock? You have some high Q reference. So you might have a cesium or a rubidium atom. And then you have a local oscillator. And you want to probe what that resonance is. And then you want to feed back and keep your laser or whatever is exciting it on resonance. Right? So all the atomic clocks on the satellites will have cesium or rubidium. And there'll be a little microwave generator that excites the atoms and looks for a microwave transition in the ground state of rubidium or cesium. And when it's on resonance, then it detects that resonance and it keeps that microwave oscillator on resonance. So we have atomic clocks that are based on 9 gigahertz or 3 gigahertz frequencies that we can count directly. Exactly what that frequency is stays on a resonance with this a particular transition in cesium or rubidium. Next generation clocks are going to be based on optical transitions. So rather than having a transition in the microwave region at 9 gigahertz, it's now possible to have a transition on the order of 500 terahertz with the same precision. Right? But now things are ticking much faster. It's oscillating at 500 terahertz instead of 9 gigahertz. Right? So you can divide up time much more accurately. And I'll tell you in closing how they do that. But what does that enable you to do? Well, we have a clock that has a stability, or you can think of it as an optical resolution of a part in 10 to the 18th. You see all sorts of weird effects, and one of them is what's called the gravitational redshift. And that's just the prediction that a clock is going to tick a little bit differently depending on the local gravitational field. So if you were to have a clock that's accurate in a part in 10 to the 18th, and you raise it up 10 centimeters, that last digit's going to change. So you're now at the level where you can map out the gravitational variation of the Earth's gravitational field, and start to see those effects. Right? So they can be used as precision sensors as well. So the frequency comb is a tool that has enabled these optically based atomic clocks. If you have something that's ticking at 9 gigahertz, you can get a frequency counter, and you plug it right in, and it'll give you 12 digits and tell you exactly what that microwave frequency is. But if something's oscillating at 500 terahertz, up until about the year 2000, there was no way of counting what that was directly. Without a huge effort, there was one exception to that. But we can't count 500 terahertz directly with electronic counters. And the femtosecond frequency comb is sort of the missing piece of the puzzle on connecting the microwave to the optical domain. And that's what's enabled the development of these optically based atomic clocks. So let me just give you a feel for what that is. We talked a little bit about just a continuous emitting laser. Right? So at a visible wavelength, it's oscillating, electromagnetic field's oscillating, and one oscillation lasts about 2 femtoseconds. Instead of a CW laser, like this, let's just look at a portion of that CW laser. Right? So now we have a short pulse, but it's at the exact same frequency. It's just a very short pulse of light. Now, in this side, we have the frequency spectrum of this light field. So here it is in time. It's a single frequency. Right? So this is what the spectrum would look like, a delta function. Right? One single frequency of light. Well, now we're going to look at a pulse, and so we still have a single frequency, but it has this envelope over it, so it doesn't exist very long. Right? So the spectrum for that pulse would be at the same frequency, but it's going to be broader. Right? Why is that? Well, there's a Fourier transform relationship between the light field and what the frequency is. Right? So if we have a short burst of light in the Fourier domain, we'll have a very broad spectrum. So the shorter the pulse, the broader the spectrum. But what if we don't have a single pulse? What if we have a pair of pulses? Right? Well, each pulse will have the exact same spectrum. So it might look like this. If you have a really, really short pulse, the spectrum can be so broad that it covers all the colors in the visible spectrum. It looks like a rainbow coming out. Okay. But it also has a phase, turns out. Right? And it turns out, because of this delay in time, the phase is going to be dependent on this period between one pulse and the next. So although you have the exact same amplitude for the spectrum, there's going to be a linear phase shift between the two spectra. And now you can get constructive-destructive interference between these two spectra from each pulse, and you get what's known as spectral interference fringes. Okay. This is a lot like the two-slit diffraction pattern, it turns out. That two-slit diffraction pattern also has a corresponding Fourier transform relationship you learn about in optics. And that's what we see here. We have two pulses, we take the Fourier transform, and we have what looks like two-slit interference. But in a laser that emits a bunch of pulses coming out of it, we don't just have two pulses, we have this infinite train of pulses. And the same thing just happens over and over and over. So these positions of constructive interference just start to get narrower and narrower. Right? So if we have a pulse train, we end up getting a lot of these little delta functions that look like teeth of a comb. Right? And they're precisely equally spaced. It turns out it's just 1 over this period between the pulses. And this is the basic idea behind a femtosecond frequency comb. That if we have a really well-stabilized train of short pulses, we can generate a comb of frequencies. Looks like a bunch of single frequency lasers. But we know exactly what the spacing is between them. And it also turns out you can relate by counting what this frequency of the pulse train is. So they're coming every 10 nanoseconds. That's 100 megahertz. You can relate that directly to what these optical frequencies are. So by counting the frequency of this pulse train, you know what the optical frequencies are, and that's connecting now the microwave to the optical domain. This actually, the realization of this resulted in part of the Nobel Prize back in 2005 by Ted Hench and Jan Hall. And you might look back and think, well, that's just a simple Fourier transform. If you've encountered that already, why is this such a breakthrough? Isn't it obvious that it should be the case? And it's always obvious in hindsight. But the outstanding problem was really the fact that the pulses coming from a laser aren't really identical. Right? From one pulse to the next, they can have a different phase. This carrier phase of the light field can be different from one pulse to the next. And that makes sense. In a laser, the pulse is going around, and the envelope travels at the group velocity, and carrier frequency travels at the phase velocity, so it might change each round trip. And the other question was, is there a fixed phase relationship from pulse to pulse? Does that get dephased? So they solved that problem on how to measure and stabilize what that is. And so it turns out that if there is a phase shift from one pulse to the next, that just shifts your comb, the frequency comb, over a little bit. And so they were able to measure that and determine what it is. And then, in the end, they got this nice relationship where any comb tooth, the optical frequency of any one of these comb teeth, is just related by the repetition rate of that pulse train, and then this little leftover piece called the offset frequency. Okay. So I'll just skip to the last part here, since we're talking about atomic clocks, and tell you this is sort of the basic components then of the next generation of atomic clocks based on optical frequencies. And that is, you start with we call it the local oscillator. This is a highly stabilized laser. And then you have some atomic transition you're trying to isolate, so you might have to laser cool the atoms so they don't bump into each other. And you have a very narrow resonance in the atoms, and you lock your laser onto that, and you feed it back so it stays on resonance with the atoms. And the problem has always been, well, how do we count the frequency of this laser now? Right? It's 500 terahertz or so. And all we have to do these days is pick off a portion of that light and compare it with this frequency comb, this highly stabilized train of pulses. And there's techniques then we count what the repetition rate of the laser is, and we compare the frequencies of this laser with that of the clock laser. And you can directly measure now these optical transitions with the same accuracy as you can with microwave transitions. So that's sort of the next, that's the basis for the next generation of atomic clocks based on optical frequencies. And there have been tremendous demonstrations in research labs. There's a big push now on trying to figure out how to engineer these quantum systems such that you can actually make them transportable. And there's a lot of active research in that area right now. Happy to tell you more about that if you want to stop by any of the lab tours later. All right, I think we have a break now, so that's it for me. We'll see you around. Thanks.
Eh, Should we start? Okay. Yeah.
Go ahead and I'll start the next session. Although sometimes we get excited, pause the breath like me. Please stop us and ask questions along the way.
Yeah. So let's do it in the informal way. If you have any questions, please stop me and ask the question. Okay. So my name is Con Q, and I'm actually originally from Vietnam, and my path to lasers has been quite interesting. So when I finished high school, I won a scholarship, right, to go to Russia to study. And then there was 10 of them, right? And then they said, we need, somebody to learn about lasers because nobody had formal training in Vietnam at that time. So they said, okay, so we have some spot for laser, and then we also have a very long coastline, right? If you know where Vietnam is, they say, okay, we need also shipbuilding. They learn how to do that, right? So they said, okay, so 3 people on the top go study laser because it's more difficult, right? And then 7 now go study shipbuilding, right? So I was lucky enough to go into the laser field by that by luck, and I love it. You know, it's a field that I've been working on for almost 20 years now, and there's still a lot of things to learn about, right? So, and for this event, they talk about lasers. I say, wow, it's so broad. I don't know what can I talk about here in the short time. When I was in undergrad, I had a class called lasers, and it was like 3 semesters long, right? Like, first we learned about laser physics. Jason gave really nice lecture about that. So you guys are expert now in laser. And then we would go into, each laser type, right? How to build them, what are the main characteristics, how to use them, and so on, right? And then the last section would be laser technology. So you use laser for precision measurement. You use laser for material processing and imaging and so on. So it's a lot of things to cover. So today I'm not going to touch into very tiny little bit of lasers. So that the overview here, I have some brief introduction and then some brief history. It's quite interesting to learn about how the laser happen. And then some of the main laser characteristics and laser type. And then different modes of operation of a laser. And then I would talk more about my research in fiber lasers, that very briefly, because of time. So hopefully after this you get a general idea of what laser is, and what type of laser are available, and what can you use that for. Okay, so this is like 100 years of laser history. So the starting point, of course, that Einstein predicts simulated emission, right, in 1916, like more than 100 years ago. That's the beautiful phenomena. And sometimes when I think about it, I'm still amazed by how that can happen. And then 30 years later, we have the major invention, right, by Charles Tau there. And then the laser itself, here I show that Charlot and Tau proposed the laser, but there's actually another person who claims he invented that too, right? So I have a slide about that. And then Neumann built the first laser in the 60s, right, 1960s, over 50 years ago. And it's a big event. In hindsight, when I look at the physics and how laser works, it's actually quite simple. You can build that easily, even in your home now. But that was a big event. And then all kind of other lasers came afterwards. Like the Heine lasers that we use a lot for alignment and for precision measurement. And then the semiconductor lasers that very compact and very efficient, right? You just run current through it and you get laser beam coming out. So at this time it was running at cryogenic temperature, so it's not really useful. It became very useful when Anfer built the first heterostructure semiconductor laser that can run at room temperature, right? And basically, that's the light source that we use right now to run the internet, right? So all the signal that we have right now running through the internet that all come from this diode laser. And then, of course, we have the laser printer, right? So after the invention, people start to find the use of laser. So laser is a really great tool. Now you start to put it into different application like printer and then fiber optic communication networks. So that all run on lasers now and optical fiber. And then we have the CD and DVD player. I don't know, you guys might not even know this already. Is this old technology? But in my years, this is a great thing, and people used to have this Walkman CD player, and and if you have it, it's pretty cool. And then we have the TISAP laser. That's a femtosecond laser that was built or introduced in the early 90s, and that's the laser that people use to demonstrate the frequency comb and optical clock and so on. And then the blue laser diodes, that's also an important invention, because before that time we used to have only red and green, right? So that we can build the blue components missing, so we can't make white light, right? So it took them a long time to figure out how to make this blue LED or blue laser, and then you have now 3 colors. You can make white light. You can make illumination system that very efficient and last very long, right? So that this is very brief look over lasers. There are a lot more. And contribution in laser research or related to laser research has been recognized by many Nobel Prize awards here. So this people got the award for the invention of the laser, right? It's very early. And then 61, Dennis Gable gets the Nobel Prize. So for what, anybody knows? No? Dennis Gable. That's for holography, right? So you use laser too for that. And then Bloombergen and Charlotte also got the Nobel Prize for nonlinear optics, right? And laser distribution. Professor Bloombergen was here, and unfortunately he recently passed away. And he has done a lot of beautiful work, and I really admire what he has done for the field. And then in '97. 20 years ago, Stephen Chu, Coherent, and Phillips got the Nobel Prize. So anybody know? Maybe Jason mentioned about it. Yeah, for laser cooling. You can use a laser beam to cool down atoms to very low temperature, right? And then Anfiorab and Chromo, that's for the diode laser working at room temperature, right? That's the basis of a lot of things nowadays. And then Ted Hansen and John Horn for the frequency comb that Jason already mentioned. And then this for the blue diode laser, right? So our blue light source there. So, and I think there would be a lot more. Maybe one of you guys would be the next. You never know, right? So what is a laser? I'm actually holding 2 lasers right now, right? So that one right there, and there's another one. So in my mind, a laser is a device, an optical device that emits a coherent beam of light, right? So that's the device that emits light, right? But that is a spectrum type light. It has to be coherent, right? Our lamps here also emit light, but these are incoherent light that we have. To understand coherence, it's actually simple in some sense, but it's actually quite complex. So if you think of light at waves, right? Coherence might mean that these waves have the same phase, have the same frequency, let's say, right? So if you have one wave and the other wave that go in sync, right? So this can be thought of they are coherent mutually, right? Or if you have 2 laser sources at 2 different points right here, if they are coherent, meaning you can if you put them to an interferometer, you can see the fringes, let's say. So because of this coherence property, you can do a lot of interesting things with lasers that hopefully you can see later. And there are so many different kind of lasers nowadays. You can have the one that that's small that I'm holding right now. You can have crystal-based laser. You can have fiber-based lasers that light's actually being guided inside an optical fiber and can go around the loop and get amplification and so on. And you have huge laser like the lasers that they are building at the Livermore National Lab, right? That for fusion energy. Not sure it's successful, but I think they are still working on it. But a laser would be fit in a building of this size, right, or even more. And we have tiny laser. We call it nano laser. That is like less than a micro now. So there are quite broad variety of lasers out there. They put out different wavelengths. They put out different power. They put out different point duration and so on, right? So all of them, the working principle is actually the same. Like what Professor Jones already told you guys, that the process is based on stimulated emission, right? So when you have an atom in the excited state, there's a photon that kind of matches that band gap energy. That photon can stimulate the transition, and then now you get two photons that are identical. That is the beauty of this. Same polarization, same wavelength, right? Same direction. And I don't know if there's any even time delay between the transition or not. You have a photon going through the atom, and basically you generate an identical twin to it, right? So now if you imagine you have a lot of atoms and this guy can go back and forth, you can basically build up a very, very large amount of photons that are identical, right, in the laser cavity. And then when you make one mirror that kind of partially transparent, so you can get some of that light out, then you have a laser beam that's coming out like here, right? And that laser beam is actually the same things that live in the cavity. That's why it's coherent, because it's the same thing that go back and forth, right? And then at each round trip, you get a little bit of it out. So that's why downstream, when you do measurement, you have coherence because it's the same thing. It came from the same source that live in the cavity. So that's why the cavity is really important component there. So the light bulb here, it's spectrally broad, right? You see it white, so that means you have a lot of color into it, and its divergence is going in all direction here. And if you take a lens, you focus it down, you can't really focus it down to diffraction limit, or like a micron or less than a micron or so, right? And then the efficiency is lower, and it's incoherent, right? Because each photon are not correlated to one another, let's say, or each of the waves that are being emitted are not correlated, right? So when you do measurement, you don't see coherence property. With laser, then a lot of time it's monochromatic. It's very narrow band, right? So you see here that green color, you see here that the red color is not a broadband white light source at all, and it doesn't diverge that fast, right? You can send it to the moon, and you can still get some back, and then you can focus it really tight. So if you put a lens in here and you size a laser beam to it, and you can get to like less than a micron, so you can condense all of this wave or all of this photon into a very small spot. So that's the reason why we can use laser to cut meron, for example, to vaporize things, to do material processing, right? And this can be extremely intense, right? Because you can have a lot of atoms in the cavity, and then you can extract a lot of photons out that way. And it's spatially coherent and temporally coherent. So if the temporal coherent is actually easier to understand. If you take a laser from this point and a little bit later you take that out, and then you do interference between the two, you can still get that interference, right? After some time. So that tell you about the coherence in time. In space, meaning if the beam here have some finite site, and if you take two pinhole and you take a portion of that beam from different location, and you can correlate them to in an interferometer. So what is needed here, Professor Jones already tell you, you need three different things, right? An active medium, so that can be a crystal, that can be a gas, that can be an optical fiber that is doped with some active ions, and then you need some feedback. That's the cavity, right? And the cavity is really important because it creates some things that live locally inside, and then the laser beam is that basically a small part of it that you take out. So if you look at a laser, since I work with it for too long, I look at it as almost a living organism, right? You have the things that oscillating, that go back and forth. It's like the heartbeat, and then what you get out is that a time delay portion of the light in there. So and that actually I show my student a lot. This paper. This actually is the first laser paper published. It's that by Mayman, right? It's very simple. It's only one page. It's very easy to write. At first, when he demonstrated, he sent to, I think, Physical Review letter, and they rejected it. They say, it's nonsense, not good enough, right? And then he sent it to Nature, and they published it. And in current day standard, if you send a paper like this out to most journals, you would be rejected too. If you look at all the graphs, it's really crude. Paper, right? He showed that the spectrum, when the laser below threshold, is supposed to be broad, right? Like we see. So it looks kind of broad, two columns there, and then above threshold, the spectrum gets narrower down, right? So, and that's what he showed. So basically, that's the only piece of data. Right? So if you send this out in today's time, then this will be rejected for sure. So you need to do a lot more than this. Okay, but when you do something first, it can be crude because it shows the concept, right? It's open door to improvement down the road, right? So when you are on something big and important for the first time, then you can get it out quickly so people know and jump on board. Right? So who invented the laser is actually quite an interesting question. And when I was a student, I say, okay, I'll find out who invented it. Right? So because Professor Tao actually came here when I was a student, and he gave a talk about astronomy. He was a fantastic researcher, and he was looking for laser in space, right? So his idea is that actually out there in space there are a lot of laser natural systems that form in the star. And in my mind, if you look at the laser construction, you need three components. Our sun actually a big laser up there if you think about it, right? So you need the gain medium, right? So you have all the hot gases. The electrons are mostly in the excited states, right? So you already have a gain medium there. Right? The pump is come from the atomic energy, right? The fusion energy up there. So you have the pump, we have the active medium converted, up converted, and then we have the cavity too, right? If you look at the sun, it's rounded, right? So light can go around, right? So sometimes when I look at it, I say, oh, actually, that could be the big laser that shining at us every day, really, right? And if you come from the east, you should like our weather here, right? It's, now because it's so cold up there now. So if you look at the laser invention history, it's actually quite complicated, and these are the few names that I found, right? So Giotto, Charlot, and Gordon Gould, that was his former student, and then Nikolai Basov and Alexander Prokhorov, that's from Russia. So they got the Nobel Prize with Professor Tao for the laser invention too, right? And then we have our Nico Bloombergen too, because on his 90th birthday, one of his students came and gave a talk here, and he actually showed a pan, a laser pan, that actually dated in '57, so it's quite early. So and then in the literature, Professor Tao actually wrote a book about how the laser happened. It's a really nice book to read. I would strongly recommend you guys to take a look if you have time. And then from the side of Gordon Gould, there's also a book too. So it's written by a writer, but he tells the story from that side. When you read this, it's kind of okay, it's not clear, but then at the end, what I tell myself, because okay, whoever invented it, we are grateful for that, and that not so important anymore. The important thing is that we have the laser and we know how it works, and we still working with it, right? So this is the thing that well known, right? So the laser was invented by Professor Towles, and that works in the microwave regime. But the working principle is almost the same as the laser. You need a gain medium, you need a cavity, and you need to have a pump external energy source to excite the molecules. And that in one of his lab books, right? That's the description of the laser, how it works, and so on. I show this to my students because they don't keep good lab books anymore, and like sometimes when we want to look back to see what they have done, it's difficult to understand. So before, when you do something, you write a description, and you write what the idea is, and so on, and you actually have to give it to another person, independent person, to read it and then cite it, right? So they read, understood, and then cite and date it, right? So that was a legal document, right? That have date and time and so on, right? So this is nobody can argue, and this is actually from Gordon Gould, and this document is interesting in a sense that this is the first time that the word laser happened ever, right? In history, and that like a beautifully written page. The description is basically the description of a cavity, right? Because going from the microwave frequency to the optical frequency, the thing that was missing was a cavity, right? Because people knew simulated emission, people knew how to excite atoms and so on already. So he described the Fabry-Perot basically using dielectric mirrors. That was the missing piece, and he said that you can have 99.9% reflectivity. So that's the same thing that we have nowadays. Okay, and the date here is November 57, right? 1957. And then there's a lab note also from Charlotte. He was at Stanford at that time. Also describing the laser at optical frequency, all the laser, right? Laser laser working in the optical frequency there. So he also did calculation of the cavity, and he calculated how the number of atoms needed for negative temperature or population inversion and so on. And this dated September 57, right? So a little bit earlier than Gordon Gould's document. Okay, so these are some of the pieces that I found, and I would recommend you to take a look, because when you look back at the history, it's not only to learn who did it, but also to learn how they did it, right? And we can learn a lot from it. So I was lucky to meet Professor Towles at Photonics West a few years, already 7 years ago, and he was sitting inside note for people, and I was lucky to get one of them here that I'm very proud of. Okay, so on laser type, there are a lot of them, but here's a rough classification. Right? We have solid-state lasers, so typically crystal-based. You have the Ziag crystal, you have the Tysab crystal, you have, it's all polished, it's all coated, and you use mirrors to form the cavity. That's the traditional type laser. And then you also have gas laser, right? So now the active medium is some kind of gas, like the Heaney mixture, for example, or argon gas. And then we have dye laser. So these are liquids already with molecule dissolved in them, and this molecule can emit light, right? This kind of obsolete already because it's kind of messy to work with this liquid dye laser. Sometimes they are toxic too, but they actually give access to a lot of wavelengths that we can't get to nowadays. So sometimes if you want some exotic wavelength, you might still have to use dye laser. And then this semiconductor lasers that really tiny, like the one in here, that you run current to and you get a laser beam coming out. Right? It's very convenient that way. And then fiber lasers, that what we're doing a lot of research on, where the active medium is integrated inside the core of the optical fiber and laser guided inside the fiber itself. So we can actually bend the cavity and coil it and then make it into a very small compact format. Right? With this, you can't do that. Right? With the crystal-based one, you can't do that. With a fiber-based, that's what you can do. And there's almost no alignment. If you splice these components together, there's no misalignment anymore. Right? With this, you have to do alignment quite often. And then modes of operation. There are actually three main modes of operation that you can see from a laser. Right? Continuous wave, like this laser here, is that a continuous stream of light that's coming out, right? In time, if you just put a power meter to it, you would get a flat reading, like constant power, right? Coming out over time. And then in this continuous wave laser, we have single frequency laser, like what Professor Jones mentioned. These are very pure, almost like a single frequency light source that's coming out. Okay, and then we have Q-streak lasers. So these emit short optical pulses at about kilohertz type repetition rate, right? Like a second you get 1,000 or 100,000 pulses that coming out. And the duration of these pulses would be in the nanosecond or microsecond range. And the way to build this is to modulate the Q of the cavity. Right? You build up the population inversion, and then you make the cavity to be high Q, and then you emit a giant pulse that's coming out that carry a lot of energy. And these are the lasers that people use for material processing nowadays a lot. Okay. And then the last type, these are mode lock lasers. So these are femtosecond lasers that Professor Jones already mentioned. These are lasers that emit picosecond or femtosecond pulses, and the repetition rate is in the megahertz, right? Like in a second you get millions of these pulses coming out, right? But they are well spaced in time and very stable in frequency, right? That's the three main mode of operations. So now, if you see a laser, you can ask a few good questions. What's that laser? Is that Q-streak laser? Is that CW laser? Or is that mode lock laser? Right? When you get the types, then you say, oh, if it's mode lock, that means it's megahertz, it's picosecond, femtosecond, right? If you see the views, and then you can ask the next question: is that a single frequency laser, or is it a multiple frequency laser type thing? Okay, and then the next question that actually when I started, I asked myself too: oh, the lasers was invented a long time ago. Why people still doing research, right? Because the physics of laser operation, the way to build this, kind of know already, right? You need three things, and you put this together, you get a laser, right? But the answer is that we still need a lot of specs, right? Like in terms of power, in terms of point duration, in terms of wavelength coverage, we still don't have a lot of good solution nowadays. Like laser in the deep ultraviolet that Professor Jones mentioned, that very difficult to build and make. Right? Or in the mid-infrared right now, we're trying to cover from 2 to 20 micron, for example. There's a lot of application there, and we still don't have good laser in that range. Right? And when you have a laser already, people want more power. Right? So if you have 1 watt, that's good. People say, can you make 100 watt? Can you make a kilowatt? And if you make a kilowatt already, people ask, can you make a megawatt so that I can shoot things down, right? And then you look at any other aspect, wavelength, the duration of the pulse, the energy of the pulse. We always need to improve on those, right? So that's why we still do research these days on laser. Okay, so. So this is some of the current research directions that we do in our group. We do laser development a lot. We build different type lasers. So hopefully during the lab tour, you can see some of that in the lab. And then we also do applications. We do nonlinear optic, like supercontinuum generation. We do nonlinear biomedical imaging. So that's the topic that I will cover a little bit more. I won't have time to cover other application. But the main platform that we are using is actually optical fibers. In my mind, it's actually a great platform because you now trap light in the core of the fiber, and you don't let it out, right? So you don't have to do alignment. You can make the laser very compact. So the history of fiber laser is actually quite old too. The first laser was demonstrated in the 60s, right, 1960. The first fiber laser was published actually 3 years later by Schnitzer, but he was way ahead of his time. So it have the same component. You have the fiber here, and that's the flash palm, right, to excite the gain medium inside the core of the fiber. And then the cavity would be at both ends of the fiber itself. It will show that it can work in that format. And then the advantage of this is that you can get very high efficiency. Our fiber laser now can give you 80% optical to optical conversion efficiency, or from electrical to light. You can achieve about 50% nowadays. You can imagine, you put in, let's say 10 watt of electrical power, like a little light bulb, and we get 5 watt laser beam coming out that can burn stuff already, right? And then this can be air cooled because in optical fiber you have the volume to surface area, right? That's really high. So the cooling is almost by air. You don't need to run water to your fiber. And it can be compact because you can coil these things together, alignment free, low cost too. Because when people put optical fibers, they can put kilometers at a time, right? With crystal you have to polish, you have to make one by a time. But with fiber you can put kilometer, and then in the laser you use only a few meters. Also, and then you can have really high power operation. One of the highest power laser nowadays that you can achieve like 50 kilowatt, 60 kilowatt already. But there's some disadvantages, right? It's a long gain medium, so it has huge ASC, and if you're not careful with it, you can burn your diode easily because that can go back to your pump. Right? And you have high nonlinear response because light is really confined in like 10 micron or so core size of the optical fiber, and you propagate over long distance. You see all kind of nonlinear optical effects, Raman, Brilliant, all kind of things. And then you have polarization instability too in the optical fiber. Okay, so these are the challenges that when we build fiber laser we have to deal with. So fiber laser was shown in 63, right? And like 30 years later, it took off only, right? Because before that, it was low power, milliwatt range is not interesting. But during this time, people came up with a new technology called cladding pump technology. And using that technology, you start to be able to put out watt and watt of light out of an optical fiber, right? You can see the rapid increase in output power here. And in 2010, 10 kilowatt coming from a single motor optical fiber, like 10 micron size, 10 kilowatt coming out of it. It's a mind-boggling. If you focus that down to a piece of steel, you can burn through it, right? Like 1 inch even easily. So now it seems like we are reaching the limit now. 10, 20 kilowatt in a single fiber output. To get more power, now people have to build, let's say, 10 of these, and then they combine them spectrally or coherently, right, to get even higher output power. Okay, so now I show you briefly about some laser applications. So this is one of the biggest application right now in material processing, right? So this is a 4 kilowatt fiber laser cutting steel, right? You can see how fast that is. You focus that down, and because the photon density so high, you can vaporize steel that fast, right? You can. The sound is off, but if you hear the sound, it's actually quite. I don't know if I can turn it on, but let me see. right? And if you look at this, this is very clean cut, right? Almost no post-processing required at all. So you can increase your manufacturing productivity significantly that way. Right, so materials that get vaporized, right? But if you pay attention to this, it's close range, right? You have to focus it down, and it's close range type work here. And if you want to look at the long range application, then that also from the Navy demonstration there, that they also use a fiber laser to shoot down things from long distance, right? That by light there. So light is actually quite powerful if you think about that, and precise too, right? You can pinpoint the things that you want to damage from a long distance that way. So you can burn a big hole through steel like that. Okay, so the next application is more peaceful, and that's what we're working on. You know, over the laptop or your cell phone, a lot of laser cutting, laser drilling in there. What you're using every day, actually, that's the result of laser technology. Right? So these are the work that I really like, and the work that we've been doing in our group. That's so-called nonlinear optical microscopy. So this is an imaging technology that allow you to go, so that MPM here, to have very good resolution and have very good section linkability. Right? So you can image one plane at a time, and you can reconstruct a 3D image that way, because your signal comes from the focal spot of the laser only. So this shows the working principle of this technology. So that's the cuvette of dye, right? So this molecule, if you shine light on it, they emit light out. And if you use 488, you focus that down, then you get emission, right, fluorescence from everywhere where that light beam is, where your excitation beam is. But now if you take a femtosecond laser beam and you focus that down, and you see fluorescence comes out only from that focal spot, very small volume, right, like 1 cubic cube, right, micron, right, one micron cube size there. And now if you move that spot around in 3D, you can get images out, right? So with this, you can go to about a millimeter or 2 millimeter deep. And then you can do even chemical mapping if you use 2 different lasers. You can map out lipid in 3D, you map out protein in 3D, and so on. So it's quite powerful technique. But the main drawback here is that it's quite expensive to get this, and quite complicated system nowadays. And what we want to do is to try to build the lasers that more compact and easier to use, and then the microscope as well for this. Okay, so for imaging, there are different modality here. So you can do second harmonic generation. So you absorb 2 photons, and then you emit 1 photon at the Doppler frequency, right? Or you can do 2 photon excitation fluorescence. So 2 photons get absorbed at once, right? And then you generate 1 photon at the shorter wavelength, that's the wavelength that you put in. Or you can do 3 photon process, and so on. So these are nonlinear optical effects that require high intensity. That's why we need femtosecond laser. And then if you do 2 color, right? You have the pump, you have stock. You can do COS, right? Coherent anti-stock imaging. And here you can map out lipids, you map out chemicals, and so on in 3D, right? So that's why it's powerful. So in our research, we developed new fiber laser system for this. We want to explore new excitation wavelength. We want to do label-free, so that means we don't want to put in any marker or anything that might be toxic. And then we want to translate that into clinical use. So I think I'm running out of time a little bit, so I go through this very fast. So if you look at the wavelength, there's a thing so-called medical window here from about 700 to 1.3 micron. That our body kind of transparent, right? You can send light through deep into our tissue that way, and that's the reason we want to develop laser in. And that's the requirement here. So that's the medical window, and there's a small wavelength there that also good to go deep in our tissue. And we need femtosecond type pulses to get the high intensity. So nowadays you can get these femtosecond TISAP lasers. So these are big and kind of bulky and expensive laser. So it's very difficult to get this into hospitals, for example, for imaging use. So what we're trying to do is to develop fiber laser instead, right? So if you look at different fiber laser now, the most popular one is around 1 micron, and then 1.55, and then 1.9. So these are already kind of too long for imaging because you have a lot of absorption there. So the way we've been working on is to use the existing platform, and then we generate the other wavelength to cover these gaps using nonlinear optics, right? Second harmonic generation, OPO, Raman, and so on to cover this. And this is the laser that we typically start. It's a handheld laser, femtosecond pulses, and then we add amplifier to it, and then we get to about like 100 kilowatt peak power. And with this peak power, you already can see a lot of nonlinear optical effects. Okay, so that's the microscope that we built here. Our student actually do all of this mechanical design. We get all the part, we put the part together, and we do all even the electronics and programming also. So it's quite interdisciplinary type of research if you want to get into. So we're actually building 2 different ones right now in the lab. And then this is the first one that we built, right? So we have the femtosecond laser. We have a scanner up here to scan the beam in X and Y direction to get an image. And then the signal will be detected by these 2 PMTs right there. Right? So, and it's all computerized, it's all programmed using software. So when I have a new microscope, it's actually a lot of fun, right? So this is the first microscope that was invented, right, in the 17th century. And with this microscope, you now can see very small things like cells, bacteria, and so on. There's actually a nonlinear microscopic wound. That's a wound that we can see only with a nonlinear microscope. That's like the microscopic wound, but it's different. So I want to show you some of this. So that's a piece of that's a leaf, right? When you put under the microscope, you see lipid in green, and you see chlorophyll in red. You can actually map out chlorophyll of the whole leaf that way in 3D with the microscope. With a standard microscope, you can't do that. Or this is actually a mosquito. The red one, that mushroom fiber, that gives second harmonic, and then the green one, that third harmonics, right? And that's the zoom in of the thrombosis of the mosquito that it used to suck your blood, right? That's the zoom in cross section of it. You can see it in 3D, and it's 100 micron or so thick there. And then we use our microscope for cancer research, also for imaging. So this for various cancer imaging, we get real sample from patient from our hospital, and then we look at those. So this patient have normal tissue right in the esophagus there. But this patient, for example, have cancer already because all the cells moving around, and we can use laser beam to do that imaging with our marker there. So it's very fast, right? It's save time. And then we have done also brain imaging. So this is actually a cross section of a mouse brain that we image. That consists of thousands of images, right? X square here, that one image, one frame, and we go frame by frame, and then we connect them all together. And this is the whole brain of a mouse there. The blue, that form the neurons, and the red, that's the intrinsic fluorescence from the brain itself of the mouse. I don't know why it's there. And if you zoom in, you can see actually individual neurons, and you see the dendrites and so on that are well connected, right? So these are the neurons, and these are the wires that connect them, right? So now we actually have a technology that can give us a way to map out the brain in 3D. So we now can basically know the location of each neurons, right? And the connection of each of them. So one image like that is like a few gigabytes. So one brain, if you think about it, even from a mouse, that is like a few terabytes. So we don't even know how to project that on the computer right now because it's too big, right? So this is my last slide here. That I just want to show you like a 3D rendering of not sure why it's not showing of the brain, because you can do plane by plane and then you put them together. You can get a 3D reconstruction of it. Let me see if I can get it to run. Maybe too big. But this was running earlier. Okay, so I'm running out of time. With that, I would like to thank you for your attention, and I would like to thank for all of my students. All of the work that I show you actually done by my student, not really by me, by you guys, right? So if you come here, you would get your hand on these things, and you make these things happen, not me or other people. You have to do it. Okay. Okay. Thank you. Any question?
Yeah, so with images of those neurons, you said that data files are really big. So at this point, you can't really do any live imaging with that?
So right now we can do live imaging, but one plane, right? We can't really get a live 3D of the brain in real time. That would be fantastic. If you can have an idea to do that, you get a Nobel Prize. Because right now, to get a brain of a mouse, right, fully imaged, it would take us about 3 months. 3 months. Go piece by piece, right? That's too long. If you come up with something that reduce that to even 1 week, people would be really happy, or even real time, right? That would be the ultimate challenge. We don't know how to do it yet. Maybe one of you guys know.
A full scan. How long? What's the time scale of taking like one plane of a mouse brain?
So right now in our lab, it's about half a second we can get one image, right? 300 by 300 micron. People have done video rate, right? But they reduce the number of points, and we're doing 1,000 by 1,000 point by a frame. People reduce it down to 100 by 100, let's say, and you can get to video rate, right? One plane. That's about the limit right now. Because if you want to go faster, you need to put more laser power. And then when you put more, it might burn stuff already, right? So we have that limit. When we do this imaging, we have to be mindful that we don't want to make things worse. We don't want to damage the tissue, right? Yeah, we don't want to burn it. Compression algorithm. Yeah, that's a good question.
Because I mean, at least with like compression algorithm, you can find a way to reduce the complexity of the image, right?
Yeah, that's what we're using. We have to use that right now, actually. Since there are different software that allow us to do that. Like, if you think about Google Map, let's say, right? You can zoom in and zoom out. That way, you get the data out when you need it only. You don't load everything in the memory. We're still learning how to do it. We're not really computer science folks. We're still learning. But that's the way to go. Yeah.
Are the mice alive as you're taking these pictures, or?
That's a good question. The one that I show you here, that already a fixed tissue, right? So that's not alive anymore. But we actually can do live imaging, and I have done that when I was at Cornell. And it's amazing because I'm not a biologist, right? When I come to the lab, my job was to build a laser and put a laser there. So I built a laser, I put the laser there, and they sent that into the microscope, and the student went into the operating room, get a mouse, and start giving it some drug or something so it goes sleep. And he can open the skull up, right? Remove some part of it, put a glass window on it, and glue it. I don't know how it works. But then he take it under the microscope, and we focus the laser beam on it, and you could see the brain working live, right? So, and we could image like that for hours and hours. You can see it working that way.
And can you see a difference in the nerves or the axons when there's an exponential going through, or when it's
People have done that. You can use this technology to do that. That's calcium potential, right? Yeah, people can see that. Yeah. So you can see the neuron working in real time that way. Yeah.
Did you use multi-photon excitation to actually do the microscopy, or do you use like OCT to actually do the light scanning?
We do the microscopy with it. So we do point-by-point scanning, right? So we focus the laser beam down, and you can think of it as the 1 micron cube type voxel, right? And then you just move it around, and then you get one plane at a time.
So did you tag it with some kind of protein, or did you just...
So the one that I show you is actually genetically modified mouse. So they generate these proteins themselves. So they change the gene, and then they produce this protein themselves in the neurons, right? And then when we focus the laser beam on those areas, we excite that protein, and that's how we can see it. If you want to see the blood vessel, for example, when I was at Cornell, we actually inject a dye into the bloodstream, and you can excite that dye, and you can see the bloodstream all over the place in the brain that way. And you can actually see the cells that moving in the entire. It was the first time that I looked at something living like that, and it's stunning. You know, it's really amazing to see that.
Do lasers usually work in one mode of operation, or is there any benefit to having them work in different modes?
Like CW and then Q-sig and then mode locking. That would be the ultimate laser, right? You get all in one. Typically, for us, we build the mode lock laser. When you crank the pump power up, you can see that 3 modes actually. At first, it would start in the CW regime. You actually get a CW laser, and you increase the pump laser limit. It actually go to Q switching, right? And you can get that. And then you increase the power further, you get the mode lock regime. That's what we want, that mode only. So typically, we set the pump power so that it go to mode lock regime, so that we use the laser beam that way. But in principle, it's doable. But if you go and buy a laser, typically you have to specify. You buy a CW laser, or you buy a Q-sig laser, or you buy a mode lock laser. They don't typically sell you the laser that can do everything. That would be fantastic, right? I never thought about that. Okay, any other question? Okay, then thank you for your attention. I think I'm out of time.
So first off, I'd like to thank Koch for coming out here, spending a few days with us to learn more about this wonderful world of optics. So it's really like luck that I got into optics.
It's coming. Paul, it's coming.
It's coming. I almost got away too much. So it really was by luck that I got into optics. I was a senior physics major at Case Western Reserve University in Cleveland. And one day a professor brought a laser and a hologram into the senior lab. And I never had seen a laser before. This is fall of 1964. I never had seen a laser before. I never had seen a hologram before. So he took this hologram, which looked like a cloudy piece of glass, and illuminated it with a laser beam. And I looked through that, and I saw a stapler. And that stapler looked so real. I kept trying to grab it, you know. I just felt it really was there. That was just such a moment in my life that I decided, you know, I really have to learn more about how holograms work. So I decided to go to graduate school to study optics. And since I hated the cold of Cleveland, where did I go to graduate school? Rochester, New York, University of Rochester. But anyway, I went there and I found out not only were holograms fantastic, but there were so many other things in optics that really were fascinating. It's a wonderful thing to work in. You know, and at that time in my life, I didn't know, did I want to be a scientist, did I want to be an engineer, or what? And it didn't really matter. If you're going into optics, you can become a scientist, you can become an engineer, you can be both. I mean, I'm still trying to figure out what I should be doing. It's just wonderful, you know. If you're interested in medicine, but you don't really want to be a doctor, a medical doctor, I mean, there's so many medical things that optics involved in. We just saw some of this in the last presentation. Do you like working with electronics? Well, nowadays, almost all the optics you work with has electronics involved with it. Computers and software, every place in optics. So it's just a wonderful area to get into. So much flexibility in what you do. And optics is really a technical enabler. It's involved in so many different areas. You know, healthcare, telecommunications, cameras, measurements, illumination, and so on. It's every place. And, of course, my favorite toy that I started with at the beginning, the iPhone. Optics every place you look. I mean, a display, optics. Camera, optics, both the lens and the detector. Now, in the iPhone 10, you know, they recognizes my face. Lasers are used to do that. The chips inside, all of them are made using optics. Internet, telephone, fiber optics, every place. I mean, this is optics, optics, optics. If you just look at in our daily lives, optics is every place, you know. Street lights, traffic lights, I should say, photocopiers, laser printers, every place, you know. And I have another slide, other places where optics are. And I have another slide, you know, other places where optics are. You know, and I could spend all my time here just showing all the different areas that optics are in. But I'd rather have you just the next few days as you live your lives, just look around you and you'll see optics is every place. Optics is every place. And the optics and photonics field is just booming right now. It's fantastic. There are a lot of optics meetings. The biggest one in the U.S. is SPIE Photonics, which is held in San Francisco every end of January. Used to be held in San Jose, but it got too large for the convention center in San Jose, so they had to move it to San Francisco. Last year, the numbers were like 23,000 attendees, almost 1,400 exhibiting companies, 4,800 technical presentations, and the meeting would be held again in 2 or 3 weeks, and I don't know what the numbers will be, but I'm sure they're going to be even larger than what these numbers are. So optics, I mean, it's been booming throughout my whole career, and it's better than ever right now. It's just fantastic. Plus, it's so pretty at times. You know, I said I got into optics because of this hologram. I saw this stapler, and it just, you know, it wasn't there, but it looked like it had to be there. There's so many really beautiful things to see in optics. And, well, a couple of years ago, I got crazy about soap bubbles, and I spent 2 or 3 weeks making soap bubbles and taking pictures. I have, you know, thousands of pictures of soap bubbles on this computer. If anyone wants to see them, I'll be glad to show them to you. But they're beautiful. They're just beautiful. The other thing, you know, do you want to work in industry? Do you want to be a university professor? Do you want to start a company? Well, the nice thing is in optics you can do all 3 of these. In fact, I've done all 3 of these. When I graduated from Rochester, I went and worked in industry. And again, I was really tired of the cold in Rochester. So where did I go work in industry? I went to Boston. And I worked for a company called iTech. And we were in the satellite reconnaissance business, really. But I had a lot of freedom to do what I wanted to do. And I had these marketing people who kept bringing problems to us and saying, you know, if you want to work on these, you can. If you don't want to, you can work on something else. But I had a lot of freedom. It was just a wonderful, wonderful time. And so I spent 6 years working at ITech. Wonderful years. But then I got a chance to become a faculty member. This was 1974. And this time the faculty position was where it was nice and warm. Tucson. Although today it's cold. I mean, I had to wear my winter coat here today. But I came out here to Tucson and joined the faculty here. And it was wonderful. It was a fantastic amount of fun. I enjoyed teaching. I enjoyed working with the students a lot. I enjoyed the research we were doing. Just, it's a wonderful life, wonderful life. But after a few years, I got, you know, itchy feet or something. I want to do something else, so I started a company. And what I want to do here, the rest of my time, is to talk about a couple of companies that I've been involved with. And I mean, I said working in industry, that was a lot of fun. I could have been happy my entire life working in industry. I certainly could have been happy my entire life working out here as a faculty member. But I have to say, doing a company was even more fun than that. Is anyone here interested in doing a company? Yeah. Of course, it doesn't have to be in optics, but optics is actually a very good area to do a company. So why would you start a company? I know. Well, one, you want to have fun. You know, it's a lot of fun. I'm not going to say every day is a lot of fun, but on the average, it's a lot of fun. Any other reason? Oh, maybe you want to make money. Of course, just starting a company, there's no guarantee that you're going to make money. There's probably a guarantee you're going to have fun, but maybe not a guarantee you're going to make money. And if you're going to start a company, you need a product. You want a product, well, something that you can make, and what's equally important, or maybe more important, something that people want to buy. And so in this case, the product started out to be an automated interference microscope for measuring surface quality of diamond turn mirrors. Now, this project did not start I didn't start it because I was going to start a company. I started because it was an interesting area to work in. I had students who needed dissertation topics, and you know, this was a possible dissertation topic. And so the idea was to use interferometry of some type to measure the surface of something. In this case, Twyman green, or maybe you've seen it called a Michelson at times. You're going to measure the shape of this surface. You get these interference fringes, and I know that you've all done this in lab. You've gotten the fringes. And it's the shape of the fringes that will tell you the shape of that mirror that we're looking at. Now, you don't want to take a ruler and measure how straight the fringes are. Somehow you want to get that data into the computer. And so how might you get that data into the computer? Well, back in the days when I was working at ITech, I noticed the following. So up the top is what? The basic equation for two-beam interference that you see. Did anyone dream about that equation last night? No. Well, maybe you will tonight. I don't know. Anyway, we have two beams who are interfering, and we get this sinusoidal, cosinusoidal interference pattern. And the thing on the right, that phi of t, is going to be some phase that I'm going to introduce between the two interfering beams, changing it with time. And maybe I'm mounting a mirror on a piezoelectric transducer and moving the mirror, changing the path, and that's giving me that phase change. What I'm trying to measure is that phi of xy. That's the phase as a function of position. And that's that will tell me the shape of whatever it is I'm measuring, whether it's a diamond turn mirror or something else. Now, if I have this interference pattern falling on a detector array, and I let phi of t be 0, this is what I would measure. And let's say I have a detector array of of 1,000 by 1,000 elements, which is very common nowadays. So that's 1 million points out of measuring this irradiance. I'll now change the phase by 90 degrees by moving that mirror, say. And now that plus cosine becomes a minus sign. Move it, change the phase by another 90 degrees, and that minus sign becomes a minus cosine. And another 90 degrees, and that minus cosine becomes a plus sign. So I measured these 4 quantities at, say, 1 million data points. Now, if I take I4 minus I2, the I sub dc cancels out, and I'm left with 2 sine of the phase. I take I1 minus I3, the I sub dc cancel out, and I'm left with 2 cosine of the phase. So I end up with a sine of the phase divided by the cosine of the phase. Tangent of the phase, take an arctangent, I get the phase. From the phase, I know what the shape of that mirror is. So when I first realized this back in my ITech days, back in the late 60s, early 70s, the idea was almost useless. I mean, we made one system using this, which had a total of 21 detector elements in it. Nothing like the millions that you have nowadays. But the problem back at that time was that we didn't have large detector arrays, and we didn't have personal computers, and we didn't have all the electronics and stuff that we really needed. So this system that we built back at the ITech days was a huge rack of electronics with 21 detector points. But by the 80s, when we were making this microscope system, personal computers were becoming available, and detector arrays were becoming available. So what had been useless in the late 60s, early 70s, in the 80s, became useful. And we built a microscope system. And this is not quite the first one, but it's close to it. It's one I have home in my garage, so I could take a picture of that. The first one I think we threw out. But, this was a dissertation project. It wasn't a company yet. But then one day, this man, so how did this turn into a company? One day, this man by the name of Bharat Bhushan came here from IBM. IBM had a large facility in Tucson, and Bharat's boss had said, well, go over to the university and see if you can find something useful that will help us some way. So he came over and had a meeting with me, and he said he brought a piece of magnetic tape, and he said, can you measure the roughness of this magnetic tape? And, when someone asks you, can you do something, what's your answer? The answer is always, yes, I can do it. I don't have a slightest idea how in the world I'm going to do it, but I know I can figure out. So I said, yes, we can do it. So he gave me the tape and went away. And it didn't take very long to think, well, maybe this microscope system would measure the roughness of that tape. Now, there's one thing I forgot to tell you about this microscope system. It didn't actually work. It took measurements, but the measurements were just garbage. It just looked like random noise. It was horrible. We knew optics pretty well, but we didn't know much about electronics. And so because of that, this system, it was a random number generator, basically. That's what the measurements were. But I looked at this magnetic tape, and it looked like a random surface to me. So maybe this thing would work. And so we measured some tape samples, and lo and behold, that we could actually tell the difference between bad tape and good tape. The numbers themselves meant nothing, because it was garbage. But somehow, by some magic, we were able to tell the difference between bad tape and good tape. So Bharat came back and said, we being IBM, would like to buy one of these microscopes. Can we buy one? And I said, yes. And he said, how much would it cost? And I had no idea what I should say there. So I said, $100,000. And he said, okay. And then I said, we have started a company called Wyco, and we would, like to sell this to you through Wyco, not through the university. He said, okay. And then I said, and we would like to have $60,000 down to buy the parts to make the microscope. And he said, okay. And he left. I figured I'll probably never see him again. But in a few weeks, I got a check in the mail from IBM for $60,000. And so I was so excited. So I went to the bank to cash it. And then there was a problem. I said we had started this company, Wyco, and the check was made out to Wyco. Well, we actually hadn't started the company. In fact, we had only just very barely talked about starting a company. But now I couldn't cash a check because a check was made out to Wyco. So what do? Start a company. So we started a company. And we started to make this microscope. But the problem was, this microscope, first one we made was just producing garbage, and we couldn't send something like that to IBM. So we had to work to make a microscope that would work. And that took us more than 2 years, 2.5 years. And, every month I would get a letter. Thank goodness this was before email became so popular. I would receive a letter from IBM saying, you said you were going to deliver the microscope this month and we don't have it yet. When are you going to deliver it? And I would send the purchasing agent back a letter saying, well, I'm sorry, we were unable to deliver it this month, but we will deliver it next month. Okay. Next month comes along. I get a letter from the purchasing agent saying, you said you would deliver the microscope this month, and we don't have it yet. When are you going to deliver it? So I take the previous letter, and I change the date on it, and send it back. And this went on for a long time. And I have to say that IBM was really very nice to us. And they gave us time to get something that worked. And so we ended up, first version was this microscope here. And I have to say it worked very, very well. And we sold more than 1,000 of these. In fact, I love this so much. In my living room at home, I have a very large photograph of this microscope system. And we could measure diamond turn surfaces. We could measure magnetic tape. We could measure magnetic recording heads. We added a lot of features to this, so we could measure all kinds of things. There were a lot of different models that we made, and just showing measurements and so on. But it really worked, and it would measure down to sub-angstroms. Now you had the optical spatial resolution, so you're not measuring atoms because you're averaging over the area disk diameter, but it could really measure heights down into the sub-angstrom region. And we sold a lot of these. We had a lot of different models, and we sold these in a lot of different markets. But the primary market ended up, where the money was made anyway, was on magnetic recording heads. So the timing, this is back in the mid-'80s to late '80s, early '90s. Everyone was getting a personal computer. Every personal computer had a hard disk drive in it. Every hard disk drive had several recording heads in it. And the industry had to measure every single one of those recording heads. And so we sold lots and lots of these. We essentially had to market for the entire world for several years until competitors came along towards the end. But it was wonderful. So it was using optics, using what I've been working in my whole life, starting a company, growing it, and then finally decided to sell it because I wanted to come back to the university. Well, before I do that, I want to, not all projects worked perfectly. That was great. But I want to show you one that was the biggest disaster we had. One that cost a lot of money. But I tell you, it was so much fun, it's well worth the money that it cost us. And this, maybe you've seen this before. If you project lines on something, and then you view where these lines intersect the surface from some other angle, it gives you something like an interferogram. And we could, do the phase shifting stuff, and we could measure all types of things. And the sensitivity of this you could vary by changing the spacing of the lines or the angle that you project them at or angle you can view. Very, very neat topic, and been known for a long time. It wasn't something we invented. But we made a very good system for measuring things. And we measured things like cans, Coke cans. Never found anyone who wanted to buy one of these systems to measure a can. No. We could measure hands very well. Measure, shape of your hands. No one wanted to buy that. You could measure feet. There was a guy who wanted to buy this. He came to us and said he wanted to measure something, but he wouldn't tell us what it was. But after long conversation, we found out he wanted to measure the shape of people's feet for making orthotics from that data. So this sounded wonderful. So we did a joint venture with him, and we built an instrument for measuring the shape of feet. And it worked well. Oh, it was fantastic. It just worked so well. But there was one problem with this. And that one problem was that for us to make a reasonable profit, we had to sell this for $12,000. And the people who wanted to buy these, and there were a lot of people who wanted to buy them, but they wouldn't pay more than $2,500 for each one. So as an end result, I don't know, we sold 3 or 4 is all. Complete disaster. But it was so much fun, that it was well worth it. Now, I just happen to have a couple of these foot scanners home in my garage yet. And I don't know if anyone here is interested in buying one or not, but I can give you a special deal later today if you're interested. Okay. So anyway, doing WICO was a lot of fun. The name WY came from my name. KO came from the former student's name, Koleopoulos, and it was a lot of fun. What's most important is you want to have a product people want to buy. You have to be willing to do whatever it takes to get the job done. Good at hiring people. Good timing, and the most important thing of all, be lucky. Okay. So anyway, I sold WICO and came back here to the university to join the faculty, and then shortly after that I got a chance to become the head of optical sciences. And so I did that for 13 years, and that was a lot of fun. But the truth is, doing companies is a disease. And I had to get involved in another one. And if I go back to the WICO days, the biggest problem we had with our products was vibration. And how could we get around the problems of vibration? So I put together a research group, and we worked on that. We came up with some ideas, and we published some papers and stuff. But none of these ideas were things that would be commercial products. But then I heard about this company in California that had a way of doing these measurements where vibration did not bother them. So I flew out to see them, and what they had was fantastic. Basically, it was a way to get all 4 phase-shifted frames at once. I don't really have time to go through just how they did it. But it was very clever. And it was a fantastic day. Vibration just did not bother them. And, the fringes would jump around like crazy, but there was a fixed phase relationship between them. So everything worked fine. And they could measure things that, not only things that were vibrating, but things that were changing shape with time and measure how it changed. Oh, I loved this. So we went out to lunch, and I said, I have to have this. I can't live without it. So I made an offer to buy the company. It was a small company, 2-person company, and bought it. We moved it to Tucson here, and it's down by the airport, called 4D Technology. And we have a lot of different products now. And of course, as a, you know, the system that I showed how it worked, although I didn't describe it, I mean, it did everything I wanted to do at that time. But once you get, I could do what I wanted to do at that time, then I got other things I wanted to do. And so then we had to invent some more, and we changed the whole technique. But it really has worked out very well. And, you know, it's good for testing large optics. This is testing in an environmental chamber at Ball Aerospace. This is testing on a polish machine that was over in Europe. You know, if you have, you could measure changes in refractive index. You could measure air streams. This is just a glass of water that we dropped 1 drop of alcohol in, and then it kind of bubbles around, and we could measure how the height changes and so on. There's a lot of different areas that we're selling this into, but the one area I wanted to mention here was for the James Webb Space Telescope. Probably everyone here knows about the Hubble, and going to be a new space telescope up there in another year plus a little bit called the James Webb Space Telescope, which is going to be, that's the size of the Hubble, that's the size of the James Webb, 6.5 meters in diameter. And the James Webb had a lot of challenging optical testing requirements. And so the people at James Webb came to us and knew what we were doing at 4D, and they said, can you do things like, can you measure the primary mirror figure? There's a back structure, I'll show you in a minute what I mean, segment phasing, thermomechanical strain, vibrational dynamics, and so on. Will your instruments measure that? And what do you say when someone says, can you do something? Yes. And then you figure out how to do it. And we did. And so, you know, we've measured end to end of a telescope system. We've measured the primary mirror. We've measured the secondary mirror. We've done this at high temperature, low temperatures. We've measured the entire telescope, including the edge, errors at the edge. We have, so this telescope is made up of many different segments, and they have to be phased so they act like a single piece of mirror. And our instruments would measure that, tell you when it's phased. There's this back structure, which is kind of weird. And it looks like something you wouldn't use interferometry to measure, but you can. And they want to know, how does this shape change as the temperature changes or as you put mechanical load on it? And again, our instruments could do that. And, you know, we could measure the segments together, and this is looking at the completed system. This is at Goddard Space Flight Center. And over here, can't see it very well, but that's our instrument over there. So I mean, and there's many, many other things we do at 4D. And, you know, maybe sometime in the future you can come down and see what we have. But it's, you know, it's a lot of fun. It's a lot of fun. As the problems come along, we solve them. We have a lot of our former students work down there now. And so, you know, in conclusion, I can say, you know, that a career in optics and photonics can indeed be a tremendous amount of fun. Now, it's not, you know, I'm sure it's not perfect for all of you, but I would guess it is nearly perfect for several of you. So at least think about it, look around, see where optics is used every place. Listen to the talks. You're going to find out a lot of different areas of optics in the next few days here. And visit the labs and give a thought to having a career in optics. With that, I will say thank you. Now, I don't know if I have any questions. We have lunch. That's probably I have a question. Where is lunch? Oh, won't be hard to find then. Okay. But anyway, thank you.